The next speaker is Professor Lu. The title is Polynomial Integrable Systems from Cluster Structures. Please.
Thank you very much. First of all, I'd like to thank the organizers for the invitation, and I'm very sorry that I could not be there in person. I'm also extremely grateful to the organizers and then to some colleagues for swapping the time slot due to my very difficult traveling schedule. Thank you very much. So the talk today will be polynomial integrable systems from cluster algebras, joint work with Yanpeng and Yu. There'll be basically 3 parts of my talk. After a very brief introduction, I'll explain a general construction for polynomial integrable systems. And our construction will be mostly applicable to a situation where you have a cluster algebra. So connection with cluster structures. And then I'll end with some examples. Okay, so general construction and connection with cluster structures and examples. Okay, so first of all, let's just very briefly recall, and I think this was already in the previous talk, but I'm on a Poisson manifold, n-dimensional complex Poisson manifold. And so therefore we have a Poisson bracket on the sheaf of holomorphic functions. And the rank is by definition the maximal dimension of the symplectic leaves. Then we have a very fundamental fact, the starting point is that if you have m functions which are independent in the sense that if you wedge up their differential one forms is not equal to 0, I'll say they are independent. And if they pairwise Poisson commute, then this m, there's an upper limit for this number m. The m has to be no bigger than n minus half of the rank, which can also be broken into the number of Casimirs, independent Casimirs, plus 1/2 of the rank. If you're in a symplectic manifold, then there's no Casimirs. Okay, just half of the rank. This number m has a name in the literature. This m is called the magic number. That's in some literature. It's called magic number of the Poisson manifold. So therefore, the definition that I'll use for today, this is also called Liouville integrability. If the magic number is m, then an integrable system on the Poisson manifold, by definition, is a set of m independent holomorphic functions which pairwise Poisson commute. Okay, so this is the definition of an integrable system on the Poisson manifold. I'm in a complex situation. Okay, I'll be concerned with a particular case today where G is a finite dimensional Lie algebra over a field of characteristic 0, let's say C, and then on the dual vector space of G, the dual vector space of G carries a linear Poisson structure. It's denoted by pi kks, such that it's a unique Poisson structure such that the linear functions, which are elements in G, have just the Lie bracket on G. And this is also called the Krylov-Kosten-Suriel Poisson structure. So it's denoted by pi kks. Okay. So it's linear. The Poisson bracket between linear functions are again linear. So as an example, let's say we look at the Lie algebra GLN and identify with this dual space by using the trace form. And then we can regard the linear Poisson structure on the dual vector space just as a linear Poisson structure on GLN. So if the entries of the elements in GLN are xij, then it's linear. So the bracket between those coordinate entry functions is just given by this formula, where these are the delta functions. Okay, so that's an example. I'll come back to this example at the end of my talk. So there's a famous conjecture called Mischenko-Fomenko conjecture, which was proved in 2004, which says that for every, suppose your Lie algebra is over characteristic 0, then the linear Poisson structure on the dual always has an integrable system consisting of polynomial functions. Okay, so this is what do I mean by a polynomial Poisson structure, polynomial integrable system. So that's a general theorem which says that polynomial integrable systems always exist. So the natural question is how to construct concretely, given a Lie algebra that you're interested in, how to compute concretely polynomial integrable systems on that linear vector space. Okay. Now there are some well-known methods I will not mention, but that's not, for example, Tim's method. That's one example. Today, what we are going to talk about is not the Tim method, although it's somewhat related in examples. It's a new method for constructing for a special class of the algebras. Okay, consider the KKS Poisson structure on the dual vector space. For a very special class of such Lie algebras, we are going to produce a method for constructing polynomial integrable systems. Okay, so that's the goal for today's talk. Okay, so let's first of all, what type of Poisson special Lie algebras I'm looking at. So let's recall a general construction in Poisson geometry. If you start with a complex Poisson manifold and where there's a point P0 where the Poisson structure vanishes, then there's something called the linearization. So on the cotangent space, you get a well-defined Lie bracket by this formula. Okay, and since this Lie bracket lives on the cotangent space, which means that the tangent space will carry a linear Poisson structure. Okay, and then so we call this pair, so the tangent space together with the linear Poisson structure, we just call that the linearization of the Poisson manifold at the point. Okay, so my goal today is to construct polynomial integrable systems on the linearization, which is but using some structure, something from the original Poisson manifold. Okay, so that's the setting. So my linear Poisson structure comes as the linearization of some Poisson structure on the bigger, on the manifold. But I need something from the manifold in order for me to construct the polynomial integrable system on the tangent space. Okay, so how do I do that? So the very brief, how do I do that? So here is the key concept. It's a very simple, but it's a very key concept that if you have a non-zero local holomorphic function on the manifold near the point P0, we can choose any local coordinates such that, so the coordinate at P0 is 0. Then for every non-zero function phi, I can define what's called the lowest order term. So it's a polynomial in the coordinates, but it's the lowest order term in the Taylor expansion. So expand it and then take all the lowest order terms, all the monomials in the Taylor expansion, but pick out those that with the lowest order terms and add them up. That's called phi low. Okay, and then phi low now can be regarded as a as a homogeneous polynomial on the tangent space. As a very simple lemma proves that it's independent of the choice of the local coordinates. Okay, so therefore every local holomorphic function, non-zero local holomorphic function at P0 has a lowest order term, which is a non-zero lowest order term called phi low, which is a homogeneous polynomial on the tangent space. Okay, that's the first starting point. Every function has the lowest order term as a polynomial on the tangent space. And then comes from the very first key lemma, which is really the beginning of our whole construction. So if you have two local holomorphic functions defined around P0, if their Poisson bracket, so this condition that they're, sorry, I'm not there yet. If their Poisson bracket is log-canonical, which means that with respect to the original pi, okay, so the bracket between phi and psi with respect to the original Poisson structure is a number times the product. Then you take the low of both functions, which are polynomials on the tangent space. Then you take the Poisson bracket with respect to the linearized Poisson structure, and that's a 0. So this is really the key lemma. This is the key lemma. Remember, we are looking for polynomials on the tangent space whose Poisson brackets are 0 with respect to pi 0. That's what we are looking for. So this lemma tells you how this is how you can get some examples. So the proof is extremely simple. You just look at the given identity, and then you expand on both sides around 0. So you expand, you have the higher order term. So if this Poisson bracket phi low and psi low with respect to pi naught is not equal to 0, you get a contradiction. Because you compare the order on both sides, and one side is their orders don't match. So that's a contradiction. It's a very simple proof. Okay, so I'd like to emphasize that this is the beginning of our whole construction. So if I have two such functions, now suppose if I want to get many, I start with functions on the original Poisson manifold. So I say I start with n functions. Okay, n being the dimension of the manifold P. Okay, we say it's pi log canonical if they're pairwise log canonical. This is with respect to pi. Pi is the original Poisson structure. Then we say that phi is a log canonical system. But when I say we add the word system, means that first of all, it's pi log canonical. System means that they are independent. Okay, so independent, generically independent. Okay, near P naught, that's enough. Yeah. So if I have n such functions, pairwise log canonical, then I can apply my previous lemma to any pair. So what we have proved then is that you take the lowest order term for every one of them, then you get n functions, n polynomials on the tangent space, which pairwise commute with respect to the Poisson structure pi naught. Okay, so that's the very first lemma or observation for this talk. Under the assumption that you start with a pi log canonical system on the original manifold, then you get a pairwise Poisson commuting set of polynomial functions on the tangent space. So this is the first key point, or I call this the first key lemma. Okay, so now let's recall that to get a polynomial integrable system on the tangent space, I need the magic number of them. So M being the magic number of the linear Poisson structure, I need that many to be algebraically independent. Okay, so when you construct in the previous lemma, after taking phi low, you cannot guarantee they're again going to be algebraically independent. Before taking phi low, they are algebraically independent on the whole manifold, but after taking phi low, they cannot be all, because remember the largest number of algebraically independent Poisson commuting functions is M. Okay, so the natural question is, can I get the right number? So if I have a log canonical system, I take the lowest order terms at P naught of everyone in your system. Does that collection contain enough algebraically independent polynomials? So that's the question. If yes, then I get the integrable system on the tangent space. Okay, so that's the question. So now before because I want to give you an example, I'll give more details of this example later on. But let's give an example just to get a feeling of what I'm talking about. You won't know at this point. I'm not explaining where this Poisson structure comes from. It's a Poisson structure on C6, polynomial on C6. Here's the Poisson. Here are the Poisson brackets. What I marked as red are the linear term. Okay, so the linearization would kill all these other terms. Would only have the red terms left. That's the linearization. That's the pi 0. And what we are looking for is a polynomial integrable system for the linearized Poisson structure. So I know I'm not explaining how, why. I know here is a pi log canonical system. So log canonical system phi, consisting of 6 polynomials, is given by this phi 1 up to phi 6. Okay, and then so just believe me that if you compute their pairwise Poisson bracket, they are pairwise log canonical with respect to this complicated pi. But then if you're taking the low, by taking the lowest order terms, here you have Z1 and here Z2. But the next time you get minus z2, so it's no good anymore because it's not algebraically independent. But for pi 4, you get a new function which is indeed algebraically independent with the previous two. And then you get from phi 5, you get this one, a quadratic one. But from phi 6, you do not get anything new. So you see that you can pick out 4 algebraically independent polynomials, like z1, z2, and then z2, z4, and this quadratic one. So indeed, the magic number for pi naught is indeed 4, and then the integrable system I pick out of this will be this 4. Okay, so this is is an example of what's coming up, an example of a general theory. Okay, so for those of you who probably know, this comes from a cluster structure on a Schubert cell, so which I'll explain later on. Okay, so to prepare for the main construction, the main theorem, I will also need to take the lowest order term not only of a function but of differential forms. So if you have a holomorphic differential form around P naught, I also do the Taylor expansion and then write out the lowest order terms. Yeah, then it's homogeneous. So all these coefficients have they are polynomials of degree m, and then we define the degree of phi low. So phi low is to be m plus k. So phi low now is a polynomial k form on the tangent space. So as in a special case, when mu is a function, then I'm getting a polynomial function. And this concept extends to arbitrary forms. So from a holomorphic differential form on the manifold, by taking the lowest order terms, I get a polynomial k form. And then it's well defined, it's independent of the choice of the coordinates. And this you can prove. So that's how do you take the lowest order term for a differential form. Okay, so here comes from the definition. So given if you have a log-canonical system, we introduce the meromorphic n form, the top degree n form on the manifold by this log, we call this log volume form. Yeah, and then you can take the lowest order term, which is now a rational n form on the tangent space, just by taking the low of the top and the bottom. So now this is a rational n form. And then you can talk about this degree. You can define this degree to be the degree of the top minus the degree of the bottom. Now this is an integer. Okay, so given this log canonical system phi, we form the log volume form and take the lowest order term, and it has a degree, which is an integer. Now here comes our theorem. This is the main theorem in the general construction, which says that given the log canonical system phi on your original manifold, if the degree of the lowest order term for the volume form, log volume form, is equal to 1/2 of the rank of pi 0. Okay, so this is a sufficient condition. Then by taking the lowest order term for every single function in your set, then that phi low contains a polynomial integrable system. That's the main theorem. Okay, and in this case, we give this a name. So we say a log canonical system at P naught have property I, so I for integrable system. If the degree, so if you form the log volume form, take the lowest order term. If it's degree, so I can just call this whole thing the degree of the log volume form at P naught. If the degree is the right number, if it's 1/2 of the rank of pi 0. Remember, rank of pi 0 is the maximal dimension of the symplectic leaf, which in this case will be the cohesion orbits. Okay, so this is the theorem. So if you're lucky enough to have a log canonical system, and you have a point where the Poisson structure is 0, you linearize the Poisson bracket, and you get the linear Poisson bracket, linear structure on the tangent space. How do you get? One possible way of getting a log canonical system is by taking the lowest order terms of your original log canonical system. to get a polynomial integrable system on the tangent space. So this is our recipe. Okay, so then the question is, where do I get such? So maybe let me just give a very quick recap. This is what I just summarized. Starting with a Poisson structure, and then you have a linearization at P naught, and you form this log-canonical volume form. If you have a log-canonical system, form the log volume form, compute its degree of its lowest order term. If it's equal to 1/2, if the rank is right, then I get a polynomial integrable system. Okay, so the question is, where do we get such a situation? How do we get applications? Where do we get log canonical system? And where? What are examples? Yeah, I mean, just having a general theorem is not good enough to support a theorem. So the magic thing is what I call a wonderful lemma. So you can see that the previous, this result applies very general. Okay, whenever you have a log canonical system, you can try to do this. The wonderful fact I call the wonderful lemma is that there is a situation where you get lots of log canonical systems. This is in the case of cluster structures. Okay, so I will explain in a minute, but I'd like to explain what do I mean by a wonderful lemma. Is a wonderful fact of life, if you want. It says that suppose you have your Poisson manifold carries a so-called compatible cluster structure. Okay, I'll explain what that means. Then, so a compatible cluster structure has lots of clusters, and each cluster is a log canonical system on your Poisson manifold. So that's a fact. The next fact, which is really the wonderful part of the fact, is that all the extended clusters have the same log volume form, or up to a plus minus sign, up to multiple by a plus minus sign. Okay, so therefore I can denote it by phi c. C, it refers to the cluster structure. All the extended clusters, there are going to be infinite many of them in general. They all have the same volume form. So therefore, if I take its lowest order term at P naught, I just need to check whether it has the right vanishing right order. Yeah. So because they all share the same thing, so the corollary is that if that common log volume form has the right degree at P naught, which is half of the rank of pi 0, then the conclusion is that every cluster structure in C, every cluster every cluster in C gives a polynomial integrable system on the tangent space. Okay, so that is the, we give this a name. Sorry, not yet. In general, there are typically infinitely many extended clusters. Okay, so every extended cluster gives a polynomial integrable system. If it has property, if it has the right property. Are there any questions so far? So this is the main. I can regard this as the main application in this case because yeah. So if I have a compatible cluster structure, and I get every extended cluster is a log canonical system, they all have the same up to plus minus sign. They all have the same log volume form. I just need to check once for all. If one of them has the right rank at P naught, then all of them would have the right rank. Then all of them would give integrable systems. So I need to explain in more detail. So we give a name. We say a compatible cluster structure has property I if that degree condition that is satisfied. Yeah, and then for the rest of the talk, I'll just very briefly explain what do I mean by the compatible cluster structure and the reason for the wonderful lemma. And a debate. This part is going to be just very quick, and then let's give 3 examples from B theory. Okay. So I'd like to explain very quickly. I think many of you are very familiar with what a cluster structure is. So if I will start with a irreducible rational affine variety and a seed. So then you have the field of rational functions, P, CP. So a field in the field of rational function, a seed in the field of rational function is a triple where phi is a pure transcendental basis of CP over. So it's a set of generators for the field of rational functions, and EX is the set of exchange directions, is a subset of the index set from 1 to n. M is a so-called mutation matrix. It's an integer matrix with n rows, and the columns are indexed by this exchange set. Okay, so given a seed, you can mutate. Okay, if you have phi is called an extended cluster, and then phi k. So I'll talk from that. So each phi k is called cluster variable, and those you cannot mutate, they're called frozen variables. Okay, so inside the seed, part of this are exchangeable variables. The other ones are mutable variables. The others are frozen variables. And then we can mutate. So given a seed, we can mutate. I probably many of you have seen this, how you mutate. Okay, you mutate the extended cluster. So you just change one function from phi k to phi k prime. Okay, so in the new seed, in the new extended cluster, only phi k changes to phi k prime, and the mutation matrix also changes, but I don't really need to recall because I don't need that. Okay? I don't need the formula. The important thing is, now let's look at the change from phi to phi prime. They only differ by one function. Okay, so see what happens is that if you look at this formula here, the right-hand side does not contain phi k. Okay, so the right-hand side has no phi k. And then, so that implies that if you compute the log volume form for phi and phi prime, so if you can try to compute, so if you take the log and take the differential, the right-hand side contains no phi k prime. So therefore, so this formula, because this one is, because of this formula 2, this set is equal to 0. It's just a simple calculation like that. So therefore, the log volume form for phi and phi prime is equal to is minus of each other, actually, or plus minus of each other. So that's the key point. Therefore, I have a well-defined. Sorry. So therefore, no matter, so by a cluster, so you have one seed that you keep mutating. Every seed you get, no matter which extended cluster you get after any sequence of mutation, their log volume forms would only change by plus minus sign. Okay, so therefore, for mutation equivalence class of seeds, there's a well-defined. There's a well-defined mu C, defined after sign. Okay, so that's the main part of. This actually also applies to what's called the generalized cluster structure, where the right-hand side has more than 2 terms, but also does not contain phi k. So exactly the same argument applies also to the so-called exotic or generalized cluster structures. Okay, so therefore, so now very briefly, what is called cluster structure on a variety. So if you have the mutation equivalence class of C's in the field of rational functions, this is a little bit technical. You can take any subset of the set of frozen variables. You can decide whether to invert those or not. And then the cluster algebra is defined to be the subalgebra of the field of rational functions generated by all the cluster variables, all the frozen variables, and then you're allowed to invert some of the frozen variables. Okay, that's a little technical because in the concrete situations, you need to be a bit careful what frozen variables we invert. And then the cluster structure, by definition, is an equivalence class of mutations seeds such that the corresponding cluster algebra coincides with the algebra regular functions. Okay, so this will be my definition of a cluster structure on a variety. Okay, so in particular, by definition, all the extended clusters are regular functions. Okay, that's important for us because, so they are regular functions. Finally, so then this is definition due to Gachmann, Shapiro, Weinstein. So a cluster structure on the Poisson manifold is said to be compatible with pi if every extended cluster is pi log canonical. Okay, this looks like a very demanding condition, but this is actually, so my remarks here is that what is hard to get is a cluster structure on a variety. Okay, so that for a given variety, having a cluster structure on a variety is a miracle. You might, if you know the subjects, you might have seen that there are lots of examples from Lie theory, like double Broha cells and Schubert cells and open Richardson varieties and Grassmannian and so on. They have cluster structures. Okay, now once you have the cluster structure to check whether it's compatible with the Poisson structure, that's actually a linear algebra check. So the miracle part is to have a cluster. The hard part is to have a cluster structure and then check that it's compatible with your given Poisson structure. As a result, if it's compatible, you just need to check at the one seed. If the extended cluster at one seed is pi-log canonical, then you check a linear algebra condition, and that's going to guarantee every cluster is going to be pi-log canonical. So I just want to make that remark. But it's also typical that cluster structures are of infinite type, which means that they have infinitely many extended clusters. Okay, so now let's just recall what I call the wonderful lemma. It says that if C is a cluster structure on P compatible with the Poisson structure, then every extended cluster is log canonical. So the first one is by definition. Okay, the first, every extended cluster is by definition. The second one I already proved. Okay, for one step mutation is true. The second one says all extended clusters up to sign have the same log volume form. We already proved that. We have already seen that. So that's the wonderful part of it. So if you have a compatible Poisson structure, you are equipped with, at least theoretically, you are equipped with infinitely many, in most cases, infinitely many log canonical systems. Okay, that's what we get, infinitely many, because you start with one, you can just mutate, you can get lots of extended clusters. They are all log canonical. Okay, so this is the recap of what I just have said so far. Okay, if you have a cluster structure compatible with pi, then you use any extended cluster, that's your favorite initial cluster, to compute the log volume form, and then you check whether it has property p or not at pi naught. Okay, by just computing the degree of the lowest order term of this log volume form. If it's equal to half of the rank of pi naught, then you are guaranteed that every extended cluster gives you a polynomial integrable system. So that's the result of the theory. Okay, so we sometimes need to modify the volume form and need to modify the frozen variable part to ensure this condition. In this case, we also say the modified. I'm not modifying the cluster structure, just modifying the frozen variables. For this, that's a technical thing. Okay, so my very briefly now I can just go through the three examples in the theory. Okay, for that I need to so this is standard notation: complex simple Lie group G, a pair of Borel subgroups, and maximal torus, and then the Val group, and etc. So this is all set up. And then we have a so-called standard complex and simple Poisson Lie group, okay, defined by an R matrix. This is called the standard quasi-triangular R matrix. And this Poisson Lie group is the semi-classical limit of the quantum group. This is the most well-known Poisson structure on complex and simple Lie group. So you can linearize. This Poisson structure vanishes at the identity. Then you get the Lie algebra. You get the linear Poisson structure. You get the polynomial. You get a linear Poisson structure on the tangent space. Now, what's the compatible cluster structure? And as is well known, you have double Broha cells, and the Bernstein Fomin-Zadvinsky define in cluster algebra 3 defines a cluster structure on each double Broha cell. Okay, and in particular for the open double Broha cell, you can prove that it's a cluster structure on G in the proper sense. You can think of it as a cluster structure on G. Okay, which is compatible with pi st. So this is all proved in the literature. There's a recent proof by Yakimov and Qinfan on this fact. And then our theorem is that this BFZ cluster structure on G has property I, okay, which means that it's not only compatible, but that's already known, but it's vanishing the log volume form, the vanishing of the log volume form has the right order at identity. Therefore, it has property I. Okay, I will not go through the more detail. The other example is on Schubert cells. So you consider the flat variety. The Poisson structure on G projects to a well-defined Poisson structure on the flat variety, and it's well known that every Schubert cell is a Poisson submanifold, and the Poisson structure vanishes at the center of the Schubert cell. Therefore, you can linearize the Poisson structure there, and then you have a linear Poisson structure on the tangent space at the center of the Schubert cell. In this case, on the other hand, each Schubert cell has a standard cluster structure compatible with the Poisson structure. This is also well known. And then our theorem is that the standard cluster structure on each Schubert cell has property I at the center. Again, has property I, so the volume form has the right vanishing order. Therefore, conclusion is every extended cluster for the standard cluster structure on the Schubert cell gives rise to an integrable system, polynomial integrable system. I can say just a little bit more on the linearization. We spent quite some time trying to study more details of these integrable systems here. So this is a little bit notation. So the linear Poisson structure is always a KKS Poisson structure. The underlying Lie algebra is this. You have to so you take all the positive roots that change sign under W. It's called the inversion set. It induces Lie algebra. So it's what we call NW minus. And the linear Poisson structure is the KKS coming from that Lie algebra. Okay. So therefore, our conclusion is that for every vowel group element, look at that nilpotent Lie algebra. Every extended cluster in the standard cluster structure gives rise to polynomial integrable systems on that linear Poisson structure. For that linear Poisson structure, when W is W naught, then that Lie algebra is N. Then we get Poisson's polynomial integrable systems on N. The example I gave you earlier is an integrable system on N for G2. Okay, G2 has the W naught has length 6. So that's why it's a 6-dimensional polynomial Poisson structure. Okay, so that was an example. The last one I just want to say very briefly is so the Poisson Lie group GLN has a dual Poisson Lie group, and then as a group it consists of pairs of lower triangular, upper triangular matrices where the diagonals are inverse of each other, and then it vanishes at the identity point. And then Gachmann, Shapiro, Weinstein introduced a generalized cluster structure on the dual group, which is compatible with pi, and therefore you can ask. So our theorem again says that the GSV. This is GSV generalized cluster structure on the dual of GLN has property I. Okay. As a result, you get polynomial Poisson structures on the linearization, but the linearization here is the linear Poisson structure on GLN that I just talked about at the very beginning. Okay, so here is what the Poisson. So we are getting polynomial integrable systems on GLN for this linear Poisson structure. Just very briefly, what does it look like? It's rather complicated, but it's polynomial. And then so if this is an element in GLN, I have to take f of it. So f of it is you take the first column of x, first column of x squared, put it in this as a second column. The first column x to the n and put it as nth column. This is called fx. You look at f of x, then you take generalized minors of a particular shape. So generalized minor, and then you add some Casimir function. And the theorem is that the functions defined above form an integrable system as an example of our general theory. This is not the same as the Gelfand-Zeppelin system. It's a polynomial integrable system, but it's not Gelfand-Zeppelin. And in the case when GLN equals 4, for n equals Yeah, and then I have the result looks like this. You have 3 by 3 matrix, and f of x looks like this. Then you take the 3 3 3 1, and then you take this minor, and then you take this minor. Anyway, this is just a concrete example to see what it looks like. Sorry, can you still hear me?
Yes, yes. Hello? Okay. Oh, could you switch on the microphone? Hello. Sorry, we cannot hear you now. Hello.
Hello.
Hi.
Hello.
Do you hear me?
Sorry, I think sorry, my phone there was a phone call.
Oh, okay.
Interrupted my connection. I'm very sorry. I'm done actually. That was the last slide. Yeah.
Okay. So have you finished?
Yeah, I'm done. Yeah.
Okay. Let's thank the speaker.
Am I sharing? Do you see?
Okay.
Why is not sharing? Is it sharing now? Okay.
Thank you. Professor Lu, I'm Dmitry Talalayev from Moscow State University. I have 2 questions.
Thank you.
Do you have examples with non-homogeneous functions which produces polynomial low terms integrable system? So principally, the log-canonical variables and cluster variables are homogeneous. Am I right?
Sorry, can you say it again? The lowest order terms are homogeneous.
And even the log-canonical variables are homogeneous.
No.
Uh-huh.
Let me show you this. No, let me show you the example in G2. No, the initial seeds, for example, the extended clusters, they are not homogeneous. That's why when you take the lowest order terms, you get something new, right?
Yes.
Here you can see these examples. Can you see the G2 example? There are 6 polynomials. So that's the initial cluster. So phi 1 up to phi 6, they form an initial cluster. They're polynomial functions, but they are not homogeneous.
I mean that the cluster variables, for example, on your cluster variety, they are homogeneous if you express these coordinates by the elements of the matrix in Grassmann varieties. You understand?
Right. But when you say homogeneous, you must have
from the initial variety. Yeah, from the initial variety.
Yeah, but in general, there's no well-defined notion of being homogeneous, right? If you just have an arbitrary variety and with a Poisson variety, you have a log-canonical system.
If you work with the
cannot talk about them.
if you work with the Grassmannian or with Brillat cells, there is a notion of homogeneity.
Only for some clusters, right? And you mean in the thicker also depending on in which coordinate system.
Okay.
In general, I think they are not homogeneous. There's they are not homogeneous. So on the Schubert cell, for the Grassmannian is actually also a special case of a Schubert cell. Yeah. There you do have some natural coordinate system with respect to which you can talk about being homogeneous or not. No, in general, I think there's no general definition of a function on a manifold to be homogeneous, right? Okay. Unless you are given like a C-star action or something, you have some action to talk about being homogeneous.
Okay, yeah. I have the second question, which will be more interesting, maybe. Do you have an idea of quantization of this method?
We are no. The simple answer is no, and we are thinking on that about it, and we also, we are very interested in understanding the quantization of this method.
So there is a quantum.
And the other thing,
there is a quantum cluster structures, which is reasonable quantization of this Poisson structure.
Exactly. I mean, these Poisson structures have before the linearization, yes, and there's quantum cluster structures. In this particular example, there are also quantum CGL extensions. So they have canonical, really nice quantization.
Yeah.
And then what does it mean to take lowest order term? What you should get are commutative, abelian subalgebras of the universal envelope.
Yes.
That's something we don't know how to work out yet. That's very much on our mind. The other thing is about mutation. Anyway, maybe I'll just wait if anybody asks that question. Yeah.
Okay. Any other questions?
Hello.
Hello.
I
have a question.
Yeah.
You have talked about the polynomial integrable system. So the first integral are all polynomial in your definition. So what do you mean by polynomial? When you fix a local coordinate, they are polynomial. But if you choose another coordinate, they may be not polynomial.
Oh, thank you. Thank you. Very, very good question. Because my Poisson structure lives on the tangent space, which is a vector space. And therefore, on the vector space, there's a well-defined notion of polynomials, right? On the vector space, you can identify the vector space by choosing basis, a vector space basis. Then you can talk about polynomial functions. And this is independent of which basis you choose. So on the vector space, there's a well-defined notion of polynomials. I mean, it's just in the elements in the symmetric algebra of the dual vector space. And there's not only notion of polynomial, there's also the well-defined notion of degree. Because I'm on the vector space. Yeah.
So the Poisson manifold you consider is the tangent space.
Correct. It's the tangent space to a manifold at a point. Yeah.
Okay. So your integrable system is defined on the tangent space.
What you can say is on the vector is a vector space whose dual is the dual of a Lie algebra. That's right. So the underlying Poisson manifold is a vector space, and the Poisson structure is linear, comes from a Lie algebra. Correct. Yeah. And then the first integrals that we are looking at, they are all polynomials. And there's other thing. Sorry.
So the manifold, the integrable system is defined on a manifold. The manifold is homomorphic, is diffeomorphic to Cn.
Yes. Yes, not only diffeomorphic, the underlying manifold is a vector space. If you choose any basis, you can identify it with Cn. Yeah. And the Poisson bracket between the coordinate functions are linear. Yeah.
Yeah, I see. I see.
Yeah, but not only that, in all these examples, we are into concrete examples. We can also prove that the Hamiltonian flows of every member in this integrable system, they are complete in the sense that when you solve the Hamiltonian flow, it's defined over the whole C, whole complex numbers. The Hamiltonian flows are complete. That's another feature that we can prove.
And the three examples you have given in the last part is also such case, which means they are defined on the tangent space at a point.
Yeah, but in the very last example is on GLN, just all the matrices. Like for n equals 3 on GLN3, you write an element as just 9 coordinates, and then you see the examples. These are there are six polynomial functions. Yes, it's all on the vector. Yeah, they are all on the dual of Lie algebra.
So they are defined on the
Professor Jiang, excuse me, that there are several other questions. People who want to questions. So can I move to on-site people? Sorry.
Hello.
Yeah. Hello.
Okay. So on this page, do I understand correctly that small f1, f2, f3 Poisson commute?
Yeah.
Yes. So this type of combinatorics we also obtain in some separation of variable business. So just can you repeat, please, what was original group and Poisson structure? Like it was on the previous slide, I suppose. Can you just comment one more time?
You mean where this example? Where we got this example?
Yeah, just can you quickly repeat what it was about?
Yeah, so this is on the GLN is a Poisson Lie group, and it has a dual group, and the dual group look at the Poisson structure on the Poisson dual group and linearize that identity. What you get is the standard linear Poisson structure on GLN, and then our theorem is that this GSV generalized cluster structure has property I. Therefore, every one of their extended clusters gives rise to an integrable system. So then I just wrote down one example. So here is the linear Poisson structure on GLN, and we obtain integrable systems on this for this Poisson structure. For this linear Poisson structure on GLN, many integrable systems we've only worked out in one particular for the initial cluster. For the initial cluster, I'm describing what the integrable system looks like. Not doing any mutation. So the way you do it is you take an element in GLN. So x times E1 is the first column of x, then the first column of x2 square, and you put them as columns. You form this new matrix Fx, and then we do minors of Fx. So these are the minors, the first left corner minors, and then you just count some minors, and these are the polynomials we get, plus some Casimirs, and we get the integrable system. Sorry, is that does that make?
Oh, thank you.
And then in the case of yeah.
Thank you.
Yeah.
The next question.
Thank you.
Yes. Thank you for the talk. At the beginning,
thank you.
You started with a complex Poisson manifold. I was wondering where is the first step or the first point when you really need the manifold to be complex and you cannot do it for a standard smooth Poisson manifold?
Oh, thank you. I think smooth is okay. I'm just doing Taylor maybe at least analytic. I'm doing Taylor expansion to define the lowest order term. Analytic should be fine as well. So I want to define the lowest order term of a function. So a function on the original manifold and you look at its Taylor expansion in any coordinate system around the point, look at the lowest order term. Yeah. For example, if it vanishes, if it's 0 and then no
excuse me, but
term,
we are actually behind of time. So could you? Oh, yes. Okay. Okay.
Yeah.
So yeah, let's thank the speaker again.
Thank you.